In the last lesson, we looked at how to evaluate limits using a graph or using a table. In this lesson, we are going to be learning properties of limits and using these properties with some strategies, some algebraic techniques that we might have to use in order to evaluate limits. Theorem 1.1 gives us three basic properties of limits. I'm going to jump straight into example 1 so we can see how those properties are illustrated. Example 1a, we're looking for the limit as x approaches -7 of the function 5. Well, it doesn't really matter what we get close to. If we're dealing with a constant function 5, the limit is always going to be 5. Just for a graphical representation of that, the function 5 is simply the horizontal line at y is equal to 5. I'm going to label my axes on this. -7 would be somewhere over here. And you can see as I come into -7 from the left and from the right, we're still at the y value of 5. Example 1b, the limit as x approaches 2 of the function x. Here, I'm going to just use direct substitution. I'm going to substitute this 2 in to the function that we're taking the limit of, and we simply get 2 out. And that's what our answer is. That's the second part of theorem 1.1 being illustrated there. If you're taking the limit of just x, well, your limit is equal to whatever x value you were approaching. In this case, we were approaching 2. In example 1c, I am again going to apply direct substitution. We're dealing with x cubed. We want to know what happens as x is getting close to -6. Well, let's see what happens if I just plug in -6. If I plug in -6 and cube it, we get -216. And that is the value for our limit. So throughout the first part of this lesson, the main thing I want you to keep in mind is that when you evaluate a limit, if direct substitution doesn't give us any issues, then we can use it to evaluate our limit. So the first thing we're going to be trying to do when evaluating these limits is we're just going to take the x value that we're approaching and plug it into the function. Sometimes that works, sometimes that doesn't. We'll see examples of both cases here. Theorem 1.2 gives us more properties of limits. Rather than going through these individually, I'm going to continue with the examples and we will see these illustrated throughout our examples. In example 2, we have the limit of this polynomial function. One of the properties above states that if we're taking the limit of a sum, two things that are being added together, we can separate that into two separate limits. Here we had 4x squared being added to 3, so I'm going to take the limit as x approaches 2 of just 4x squared, and I'll add that to the limit as x approaches 2 of just 3. This is applying the sum property of limits. Now, I can take this even further. In the first limit, we have a constant of 4 right there. We have a constant multiple rule, a scalar multiple rule that tells us that we can pull that 4 out in front of the limit because it is a constant. That's number 1 from that previous theorem being illustrated there. Next, what is the limit as x approaches 2 of 3? That limit is simply 3. This is just a constant function. This is the first example that we looked at. When we're just taking the limit of a constant, that will simply equal that constant. Continuing to evaluate this limit here, I'm going to evaluate with direct substitution. Okay, so I'm just going to take this 2 and sub it in there to that x squared. Gives me 2 squared. I'll add 3. So this limit is equal to 19. Okay. You don't necessarily need to show all of these steps when we are evaluating this limit. I broke it down so that you can see these properties being applied, but the reality of the situation is this limit was evaluated with direct substitution. All I did was took this 2 and plugged it in to where x is. We had 4 times 2 squared plus 3, that gives us 19. If direct substitution doesn't give you any issues, that is the most straightforward way to evaluate your limit analytically. The next theorem tells us that we can use direct substitution for polynomial and rational functions. We've already seen direct substitution working for a polynomial in example 2. Now in example 3, we're going to look at direct substitution for a rational function. As long as the denominator is not 0. Right? As long as the denominator is not 0, then direct substitution will work for rational functions. Second half of this lesson, we will look at examples where direct substitution does give us 0 in the denominator, and we'll talk about how to deal with that there. So for example 3, coming in with direct substitution, I'm going to be taking all of the x's that are in this rational function and replacing them with 1. And I'm left with 2 as my answer, and so this limit is equal to 2. The next two theorems tell us how we can use direct substitution for a radical function or for a composite function. It's the same concept as before. As long as we're not getting any domain issues, we're able to come in and apply direct substitution. So let's look at example 4. I'm going to be coming into this radical composite expression, and I'm going to substitute in 3 for x because I'm interested in what's happening as x approaches 3. So I'm going to be replacing the x in this expression with 3. And the cube root of 8 is equal to 2. Our next theorem tells us that we can use direct substitution to evaluate limits of trigonometric functions as long as we are in the domain of that trig function. So let's look at some examples. The limit as x approaches 0 of tan x. Well, 0 is in the domain of the tangent function, so now I want to know what is tangent of 0. Remember that tangent is y over x. At 0, that would be 0 over 1. Which is simply just example 5b. Let's go in and try direct substitution. We have pi that we are approaching, so I'm going to be replacing the x's with pi. So I now have x times cosine of pi. I now have pi times cosine of pi. Both of these x's got replaced with pi in direct substitution. So this is pi multiplied by cosine of pi. Think about where pi is on the unit circle. Pi is over here, and over here the x coordinate is -1. So cosine of pi is -1, leaving us with negative pi as our answer. And finally here in our last example for this part, we have the limit as x approaches 0 of sine squared x. Let's come in and apply direct substitution. What is sine squared of 0? Just make sure we're all on the same page. That means find sine of 0 and square it. Well, sine of 0 is 0, and 0 squared is still 0. So far, in all of the examples that we have looked at, we have been able to evaluate our limits by direct substitution. In example 6, we have the limit of a rational function, very similar to what we had in example 3. The limit of a rational function. In example 3, we came in, we did direct substitution, we got an answer. Let's see what happens if we try direct substitution in example 6. So substituting in 1 for x leaves me with 1 cubed minus 1 over 1 minus 1, which is 0 over 0, which is a problem. So I'm going to erase these equal signs because things do not equal 0 over 0. 0 over 0 is an indeterminate form. And what that means is that we're not able to determine what the value of the limit is from just that. It does not tell us anything about what the value of the limit is. But what 0 over 0 does tell us, what's very important about getting 0 over 0, is that it implies that the numerator and the denominator have a common factor that needs to cancel. Because when I plugged in 1 in the numerator, I got out 0. And when I plugged in 1 in the denominator, I got out 0. That means that x minus 1 is a factor of both the numerator and the denominator. We know it's a factor of the denominator. We can see it right there. But it also has to show up as a factor of the numerator. Now, what the question is then is what is left in the numerator? Because remember, the numerator was originally x cubed minus 1. And now I'm saying, well, I know x minus 1 has to be a factor of it because I got 0 out when I plugged in 1. So what's that missing quadratic? Something with an x squared goes there. Well, we can figure that out by division or by factoring that numerator. I'm going to actually go through the division. I'm going to do synthetic division on this real quick. If you have any questions about what I'm doing over here, this synthetic division, please email me. I can talk you through this. The good news is most of the problems that we do, we will very likely not be using synthetic division. So example 7 is a lot more indicative of what you can expect to see. So don't be discouraged by this. But if you have questions about it, please do ask, because we did learn how to do that back in 171 pre-calc. Okay, so we are left with, remember this started with x cubed, so now we have x squared plus x plus 1. Okay, so we have this rewritten now, and clearly enough, we are able to see that common factor of x minus 1 that we are now able to cancel. And with that common factor canceled, we are simply left with the limit as x approaches 1 of that quadratic, x squared plus x plus 1. And now direct substitution would work and leave me with an answer of 3. So after we canceled, then we were able to come over here and just use direct substitution. So what theorem 1.7 tells us is sometimes when you try to evaluate the limit, what you're actually going to have to do is you're going to have to go find another function. So you started off with one function f of x. You're going to have to go find another function g of x. Kind of like how we started off with this and we found another function after we simplified it and canceled, right? And in that other function, they're equal except at one x value. So in our case, x cubed minus 1 over x minus 1, when we did that division, it was the same thing as x squared plus x plus 1, because we canceled out that x minus 1 in green over here where we're doing this canceling. But not at 1, right? Not at 1, because the issue was at 1. But we can use this new function to apply direct substitution to the limit and get our answer. So the big takeaway from example 6 is that if you try direct substitution and you get 0 over 0, that means that there is a common factor that you need to go cancel out. Okay, that common factor, here ours was x minus 1. You should be able to tell what it is because look at what you plugged in. We plugged in 1 and we got out 0, so our factor had to be x minus 1. You may have to do some work to figure out what goes here to simplify this. You may need to factor, you may need to do some division, unlikely though. And then once you cancel that out, you're then able to apply direct substitution to get your answer for your limit. Let's look at another example. Example 7. First things first, a rational function, we need to try direct substitution. So I have plugged in -3 for all my x's. I'm going to keep simplifying this. And I am left with 0 over 0. Okay, so I'm going to erase these equal signs because things do not equal 0 over 0. But this indeterminate form in particular tells me that I need to cancel the common factor. Moreover, I know that the common factor must be, well, let's think about that. We plugged in -3 and we're getting out 0. So that common factor had to be x plus 3. And I can see it in the denominator if that's another hint if we needed it. So let's rewrite this limit. Notice that I'm still writing the limit here. The limit equals the limit. But I want to rework the numerator. I'm going to factor it. I know x plus 3 is a factor. The other factor is x minus 2. It's factoring quadratics. So now I can say that this limit is equal to the limit as x approaches -3. But this time I'm going to go ahead and cancel these out. That x plus 3 was problematic. All we're left with is x minus 2. And now direct substitution works, and we have -5 for our answer. Example 8, I'm going to start off by using direct substitution. I'm replacing all of my x's with 0, and it's leaving me with 0 over 0. So I'm going to erase my equal signs because things do not equal. 0 over 0. We're again getting an indeterminate form. It still tells us the same thing it's told us in the last two examples. 0 over 0 means that we need to cancel the common factor. And in this case, the common factor is x. Right? That common factor that you're looking for is always x minus whatever you're approaching. So in this case, x minus 0, which is just x. Over here, x minus -3, which would have been x plus 3. There's that common factor. Up here, x minus 1, there's the common factor. It's always x minus whatever you're approaching. Okay, so there's a common factor of x. So in other words, what I'm saying is that I should be able to rewrite this numerator as x times something. And then we still have that x in the denominator. There's our common factor. This should be able to cancel. And then whatever is left right here, we would use that piece for direct substitution. Now, if you're looking at this, you think, okay, well, how am I supposed to figure out what that orange box is? This is not like the last example, right? This is not something that we can just factor. This is a radical expression. To deal with that, we have a certain technique that we use, and that technique is called multiplying and dividing by the conjugate. Okay, so what does that mean? I'm going to start off with our limit. And to help me rewrite this so that we can see that green common factor of x, I'm going to come in and I am going to multiply this entire expression by the square root of x plus 1, same thing we had, but this time I'm going to put a plus 1. And I'm going to do that in the top, and I'm going to do that in the bottom as well. So this is the conjugate, what that is in the top. We multiplied by it in the numerator. We divided by it in the denominator. To get the conjugate, you do the exact same thing that you had here, but you change the sign. That was minus, so you change the sign to plus. If it would have been plus originally, we would have changed the sign to minus. Okay, so now let's actually see what we get in this new expression. So we have the limit as x approaches 0. I am not going to do anything at all in the denominator. The denominator is x times the square root of x plus 1 plus 1. I'm not going to distribute that in. I'm just multiplying straight across the bottom. I'm going to leave that as it is. And up here in the numerator, I am going to actually start FOILing things out. So FOILing this out, I would have this square root times that square root, which would be x plus 1, because the square roots would cancel. Then I would have this square root times 1, so I have a positive square root. Then I would have -1 times this square root, which would give me a negative square root. So these will cancel in the middle, right? These two things right there are the same. They'll cancel. That'll always happen. I erased my 1 over here. The last thing we need to multiply is that -1 and that +1 to give me a -1. So let's see what we are left with. In the numerator, we have x plus 1 minus 1. There's x plus 1 minus 1. That's what we have left because those two terms in the middle canceled. In the denominator, we still have this product. We can cancel the +1 minus 1 that's in the numerator. Those just go away. And look what we are left with. X's that cancel. What does it leave us with? It leaves us with a 1 in the numerator and this square root of x plus 1 plus 1 in the denominator. So we were able to cancel that common factor of x. Do not be dismayed that this was in the top and that what's left is in the bottom. They're technically the same thing. It's just a matter of how you write it. But what's important is that we have canceled that common factor of x. So now that that common factor of x is canceled, now let's apply direct substitution. I'm going to come into what's left and replace all of my x's with 0. I only have one x to replace. And I'm left with 1 over 1 plus 1, which is a half. So big takeaway from example 8 is if you have a radical expression and you try direct substitution from the start, and it gives you 0 over 0, you still need to cancel the common factor. The same way that we canceled the common factor when we had a rational expression in examples 7 and 6. The difference is if you have something that is radical, in order for you to cancel that common factor, you're going to have to come in and multiply and divide by the conjugate. In example 9, we are again going to start off with direct substitution. Come in and replace all of these x's with 0. We want to see what's happening as x approaches 0. I have a third minus a third in the numerator over 0, which is 0 over 0. Which again tells us that we need to cancel the common factor. In this case, we were approaching 0, so our common factor is just x. So I can see the x in the denominator that we're going to use to cancel, but to find the x in the numerator, we're first going to have to do some algebra. To find the x in the numerator, we're first going to have to do some algebra. I'm going to go off to the side and do this algebra. So I'm just going to take this numerator and I'm going to rework this by finding a common denominator. So I'm going to rewrite both of these fractions with a common denominator of 3 plus x times 3. So I've just multiplied their two denominators. In the first fraction, it only had the 3 plus x in the denominator. It now has a 3 in the denominator, so it also needs a 3 in the numerator. Second fraction only had a 3 in the denominator. That denominator got multiplied by 3 plus x, so the numerator must also be multiplied by 3 plus x. So now that we have the common denominator, let's actually combine them into one fraction. Common denominator will stay the same in the bottom. But in the numerator now, I have 3 minus 3 minus x. Make sure you apply that subtraction to both terms there. The 3 minus 3 in the numerator will cancel and we'll just have a negative x over our common denominator. Remember, all we did was we started with the numerator, right? I took the numerator and we simplified it, and now we're here. But now we can see the factor of x. Remember, we said we had a common factor of x. Now I can see the one that shows up in the numerator, and I can see the one that shows up in the denominator. Algebraically, it may be easier for you if you write that common factor of x alone, and then I'll put everything else that we had left in the fraction. So now that we're done just working with the numerator, this is what we have for the numerator now. Let's go back to the whole limit. So we have the limit as x approaches 0 of, I'm not going to write this in the numerator anymore. I'm now going to write this in the numerator. And in the denominator, we only had x. I'll just put that x right there. And I set it up like this because now I can see the common factor of x that I want to cancel and only be left with the limit as x approaches 0 of negative 1 over 3 plus x times 3. The x in the denominator just turned into a 1, so I don't need to write it anymore. And now, let's see what happens if we apply direct substitution. We have negative 1/6 as our answer. So we've looked at what happened when we're evaluating a limit. when we start off with direct substitution, and it works out beautifully and we get our answer very easily. We've also seen several examples where we apply direct substitution and we get 0 over 0. We have to do some algebra to get a common factor, cancel it out, and then we can do direct substitution. Now, the last part of this video, we're going to look at what happens when neither one of those two things work. To help us with that, we have some tools of some theorems that we will be using. The squeeze theorem and two special trigonometric limits. So the limits in theorem 1.9 are not anything that you would need to prove, just theorems that we will be using. I will explain the squeeze theorem when we need to use it. We'll use that in example 11. We'll talk about that in a second. Starting with example 10, we have the limit as x approaches 0 of tan x over x. Let's see what direct substitution would give us. Tangent of 0 over 0. Well, we definitely have 0 in the denominator, and in the numerator, tangent of 0 is 0. So we have an indeterminate form. I'm erasing my equal signs. This does not tell us the value of the limit. So I'm going to try to rewrite this so that I'm able to then evaluate this limit and get an answer. So to do that, I'm going to take this, the limit as x approaches 0, and what I'm going to do is I'm going to use some trig identities, one in particular. So we have tan x in the numerator right now, and just x in the denominator. I'm going to replace the tan x in the numerator with sine x over cosine x. So back in 172, trigonometry, we learned that tangent is sine over cosine. And the reason that I do that is because I'm looking at this limit rule right here. And this limit rule says if I just have sine x over x, I can say what the value of that limit is. So I'm going to do some rewriting of this limit here. Just doing some algebra to rewrite that and have that look better. That now I can see the sine x over x. So now I'm going to separate this into two separate limits. I'm going to take the limit of the sine x over x. We have a multiplication symbol here, so I'm going to break this up into the product of the limit of 1 over cosine x. This is the product rule for limits. If we have the limit of a product, then I can separate that and write it as the product of two limits. So now let's evaluate these two limits. Well, for the first limit, this is the special trig limit. That is this limit here, which is equal to 1. The second limit, let's try direct substitution. We have 1 in the numerator. In the denominator, I substitute in 0 for x, and cosine of 0 is equal to 1. So this leaves us with 1 for our answer there. In example 11, we will be applying the squeeze theorem. And first, let's just go in and try direct substitution. See what happens if I substitute in 0 for theta. I would have 0 squared times cosine of 1 over 0 cubed, which is a problem because that 1 over 0 is undefined on the inside. So I'm erasing my equal signs. The squeeze theorem tells us is that if we can bound the function with a smaller function and a larger function, and we know that the smaller and the larger function have the same limit, then we can say that the function in the middle has the same limit. Here is just a rough illustration graphically for the squeeze theorem. Let's say you have a function h of x that goes like this. And then let's say you have a function g of x that comes in and goes like that. They agree right here. Let's say they agree right here at 2. Okay. And then let's say, this function is g of x and the bottom function was h of x. Let's say I want to know the limit as x approaches 2 of a new function, f of x. Okay. Remember, these two functions are the same value right there. I don't know, let's say that that's -4. So where's the function f of x? Well, the squeeze theorem says that you could find the limit of the function f of x if f of x is in the middle. If f of x is in the middle of those two functions. So if f of x is some function that stays in between those two, and those two functions g and h were the same thing at 2, this limit also has to be the same thing at 2. That's what the squeeze theorem says. Okay, so let's see what we can do here. So what we need is to be able to take the function theta squared cosine 1 over theta cubed, and we want to get it squeezed in between two functions there. We need to figure out what are we going to put there and what are we going to put there. Let's start building that. So I'm going to start with just the cosine of 1 over theta cubed, because one thing we do know about cosine is that it stays in between -1 and 1. The cosine does not go smaller than -1 and it does not go larger than 1. So now that we have that bounded, I'm going to now come through and multiply everything in this inequality by theta squared. And I'm doing that because I want to get that function theta squared cosine of 1 over theta cubed. I want this function here. So everything has been multiplied by theta squared. So now we have something that looks like the squeeze theorem. We have a small function, we have a big function, and we have a function in the middle. For the function in the middle, we're interested in what's the limit as theta goes to 0. Well, the smaller function, as theta goes to 0, it goes to 0. And the larger function, as theta goes to 0, and I know these because I'm just doing these with direct substitution, this also goes to 0. So that must mean that by the squeeze theorem, the limit of the function that was squeezed in the middle, theta squared cosine of 1 over theta cubed, must also be equal to 0. Example 12, we have the limit as t approaches 0 of sine of 6t divided by 5t. That limit looks kind of similar to our first special trig limit, but not exactly. So let's see how we can manipulate it. I'm going to rewrite this as the limit as t approaches 0 of sine 6t over t. The 5 that I'm not writing is a constant that I can pull out as a 1/5. Okay, I cannot pull out the 6 on the inside of sine because it's on the inside of sine. Now, this looks a little bit more like that special trig limit, but the problem is the 6 that we have here, but I don't have a 6 down here. And that special trig limit says these two things need to be the same. Okay, not necessarily x and x, but they do need to be the same. So if I wanted to put a 6 down here, I would also need to put a 6 in the numerator. And I'll just choose to put that 6 in the numerator outside. Now, I could apply the special trig limit because these two things here are now the same. That special trig limit tells me that limit is equal to 1. So this is 6/5 times 1.